Beneath the abstract mathematics of artificial intelligence, there is a chaotic physical reality. Every computation is an electrical pulse navigating miles of microscopic silicon pathways. At the center of modern language models is the scale dot product attention equation. This is the mechanism that allows a transformer to determine which words in a sequence relate to each other, assigning mathematical weight to their connections. The defining feature of this equation is its n by n attention matrix. If you input a sequence of 1,000 tokens, the model calculates 1 million relationships. If you double the sequence to 2,000 tokens, the number of calculations squares to 4 million. In theoretical computer science, we use big O notation to evaluate this kind of scaling complexity. The assumption is that analyzing the total number of mathematical operations required will accurately predict how long an algorithm takes to run. On modern silicon, that assumption breaks down. Transformers hit a scaling wall because the physical layout of the processors creates a bottleneck that outweighs the cost of the raw math itself. To locate the exact point of failure, we have to map out the physical architecture of an AI GPU. The critical components are not just the compute cores, but the distinct physical pools of memory. The majority of the chip's memory is high bandwidth memory, or HBM. This is a massive reservoir, usually holding 40 to 80 gigabytes, where all the model's weights and input data natively reside. In contrast, the center of the chip houses the SRAM. This is a tiny 20 megabyte cache where the actual arithmetic happens. It is exceptionally fast, processing data at 19 terabytes per second. Because arithmetic only happens in the SRAM, the GPU must constantly transport data from the HBM across the physical chip to the compute cores. This transit cost is called I/O complexity. Pushing electrons across that physical distance takes orders of magnitude longer than executing the math itself. The compute cores finish their arithmetic in a fraction of a millisecond and then sit entirely idle, waiting for the next data packet to finish the long journey from HBM. To make a model run efficiently on this architecture, the primary objective is no longer reducing the total number of calculations. The objective is minimizing the physical distance data has to travel. Standard exact attention fails the I/O complexity test almost immediately. When the forward pass begins, the GPU reads the query and key matrices from the slow HBM and hauls them into the fast SRAM. The cores multiply them to create an intermediate attention scores matrix, known as S. Because S is typically larger than the tiny 20 megabyte capacity of the SRAM, it must be evicted. The hardware writes the entire S matrix all the way back out to HBM. Next comes the softmax calculation. The GPU has to reach back into the HBM, pull the S matrix back into the SRAM, calculate the probabilities to create matrix P, and then write P back out to HBM again. For the final step, it reads P from the HBM one more time alongside the value matrix V, multiplies them in SRAM, and writes the final output O back to the HBM. During this entire operation, the compute cores are actively calculating for roughly 1% of the wall clock time. The standard algorithm is heavily memory-bound. It starves the fastest components of the GPU, forcing them to wait while massive grids of numbers are shuffled back and forth across the silicon. FlashAttention solves this hardware bottleneck through a technique called tiling. Instead of moving entire matrices, it slices the inputs into smaller, manageable blocks. It loads tiles of Q, K, and V simultaneously, so they sit together inside the SRAM cache. But there is a strict mathematical blocker to computing attention in chunks. To calculate the softmax probability for any single token, the equation requires you to divide by the sum of the exponentials across the entire row. You cannot sum a row if you only have a single tile in memory. To bypass this, FlashAttention uses an algebraic trick called the online softmax. It allows the GPU to compute exact probabilities block by tracking two local variables, a running maximum value, m, and a running sum of exponentials, L. When the first tile finishes its multiplication in the SRAM, the algorithm identifies the local maximum value and stores it in M. Simultaneously, it calculates the partial sum for that specific tile and stores it in L. As next tiles of K and V cycle into the SRAM, the hardware checks new numbers against the tracked variables. It mathematically rescales the previous partial outputs directly in the SRAM, assembling correct global probabilities without needing to see the whole matrix at once. Because the rescaling happens locally, the intermediate matrices S and P are never written to the slow HBM. Only the final, complete output matrix is transferred. Tiling takes a problem that scales quadratically across a slow memory bus and converts it into isolated, localized mathematics that safely respect the strict physical limits of the SRAM. This I/O awareness also solves the critical memory bottleneck during the backward pass of model training. To calculate gradients, standard training requires the hardware to save the massive n times n intermediate matrix from the forward pass. When it's time to apply the updates, standard architectures execute a slow, heavy read operation, pulling that saved matrix out of the HBM. FlashAttention does something that seems counterintuitive. It discards the intermediate matrix entirely. It saves nothing. Instead of storing the data, it uses a process called recomputation. During the backward pass, FlashAttention simply pulls the original Q, K, and V tiles from memory and recalculates the exact attention scores completely from scratch on the fly. Because the arithmetic in the SRAM executes thousands of times faster than data transit, repeating the multiplication from scratch finishes long before the standard method can even pull the saved matrix across the hardware channel. On modern silicon, floating point operations are cheap and data movement is expensive. Doing the complex math twice is physically faster than reading it from memory once. The mechanics of I/O awareness translate directly into measurable performance. When the authors benchmarked FlashAttention, the empirical data confirmed the hardware theory. For years, researchers tried to solve the n-by-n scaling problem by designing sparse attention models. They aggressively cut the total number of floating point operations, hoping less math would mean faster runtimes. But because those models still required heavy read-write cycles, the real-world speedups rarely materialized. This line graph plots sequence length against memory usage. As the context window grows, standard exact attention curves upward quadratically. The hardware runs out of available HBM, triggering a strict out-of-memory failure. Plotted on the exact same benchmark, FlashAttention produces a flat, linear trajectory. Because it only ever stores the inputs and the final output, its memory footprint scales proportionally to the sequence length, easily bypassing the previous hardware ceiling. The result is a 2 to 4x reduction in total wall clock time, requiring a fraction of the memory, while returning the exact same mathematical outputs as the standard equation. By aligning the algorithm to the layout of the chip, FlashAttention effectively rendered a generation of sparse approximation research obsolete. It proved that exact attention could outpace approximations simply by minimizing data transit. The success of FlashAttention established a rigid rule for modern deep learning. Software design cannot be decoupled from hardware physics. An efficient algorithm must know exactly where its data physically lives on the silicon. Prior to this optimization, the quadratic memory requirement of the attention matrix was the definitive barrier preventing models from reading long-form text. Once that physical bottleneck fractured, the context capacity of language models rapidly expanded. The 2,000 token limits of early models scaled to 100,000, then to 1,000,000 and beyond. This is the structural foundation that allows you to drop an entire novel or a complete software codebase into a single prompt today. This specific hardware-software fusion engineered the era of the massive context window LLM, providing the physical mechanism necessary to sustain our current scale of artificial intelligence.